so that's why I'm calling it. Because yeah, so also yeah, so also you can reformulate this theorem slightly as follows. So let me do it here. That so this is precisely what is called semi-continuity theorem. Chevalier semi-continuity theorem. And, So this is corolla, but it is this important. It states the following. So you can consider the subset. So Xn is the subset where the fiber, dimension of the fiber, has. So it is a subset in X. So you start with, of course, just in the same setting as Chevalier theorem, so you have a morphism of reducible varieties. You also can think that it is dominant. Actually, you can always reduce this just the statement of any theorem, but by just a statement of this theorem by taking just a reducible component of X, taking the reducible component of the contained image, and taking actually instead of Y, you can take the closure of the image. So it is so this statements reducibility and the dominance of F are just the statements for me to be more just confident. So in this statement, so you can consider the following subset in X. So this is just the set where dimension of the fiber over X is bigger or equal than N. So the claim that it is closed subset. Xn, then Xn is closed in X. So this is quite important here because just the statement is important in order that just you cannot say this for Y, but the same statement for Y, but so it is convenient to formulate it like this. So let us derive it because it is very easily can be derived out of Chevalier.
Did you say that this is true for the x's that are in the image of F, not for?
Yeah, I mean notice that just notice that the dimension of let me destroy this theorem a little bit. Yeah, so suppose this doesn't hold. Yeah, so suppose this doesn't hold. Then you have a dimension of of the closure is less then dimension of y. Then this estimate is even better.
Ah.
So, but however, there is the second point in this theorem that says that for the open, just you have this equality, so I have to write down that dimension of x minus dimension of the closure. I mean, if you want to write down this for
And is irreducibility important for?
irreducibility is important in the sense that one component, so you restrict it to one component, so the different components can behave differently.
So we have a
So you can have two components that map to the same set, but they are not related. The components are not, the behavior is not related, so they can have different dimensions. So that's why, and you cannot keep track on these components without special assumptions, and so that's why without special assumption on x itself. So that's why it is. I mean, for just I'm saying that they reduce.
So maybe why is reducible is not important?
Yes, but I mean, I want to say that just for me it is more pleasant to have dimension of y, which is just one number. Yeah, I mean it is just for my comfort and not for the sake of.
X is reducible.
Yeah, so if x is irreducible, y can be reducible, but f of x is irreducible, yes. I mean, it can be stupid, yes, so just, you can stupidly map a line to the union of two lines. So that's why I do not want to think of the statement in this sense when I formulate this theorem. Of course, if you are thinking at the particular situation, you should understand that it can happen that if you are speaking of variety, you can have many different components, etc. So you just, it is, depends how you prefer to work with variety, which steps you do. So, okay, so let us explain this part. So, let us look at xm. So, notice that if n is equal to, so again we assume that, the closure of f of x is equal to y. So notice that if n is equal to dimension of x minus dimension of y, then there is, or if this n is less or equal than this dimension, then the fiber has, you have this equalities for the fibers, so you do not have to prove anything. So just xn is the whole set x, and we are done, so it is closed. So we assume that n is strictly less than dimension of x minus dimension of y. So then you know the following. Then you know that you have open subset where you shouldn't search for the fibers of dimension equal to n. So you know that just xn, there is open subset u in y. It is open such that dimension of pre-image is precisely a dimension of x minus dimension of y. It is less or equal than n, and so it is equal then to n. So this n was taken to be some number, so it was less or equal than n. Now we consider the case when n is bigger.
I don't understand why is
I mean n, just if n is bigger than this dimension, then the dimension of general fiber, I mean, I take the open subset where the dimension is precisely the dimension of x minus dimension. I take the subset from the theorem. So
theorem says that
there is open subset where the fibers has expected dimension equal to dimension of x minus dimension of y. So if n is just bigger than this expected dimension, then
it should be an empty set.
no. I mean, I just take any n. For example,
Sometimes dimensions are bigger than expected.
yeah, n is bigger than it. So this dimension is smaller. So you know that you do not have to search this. So this points x which belongs to xn, they have a non-empty. So they
all belong to
yeah. So they do not belong to pre-image. X doesn't belong to pre-image of u. Yeah, so they are not along this file. Yeah, so this means that xn belongs, yeah, thanks. Yeah, so this means that xn belongs to the complement of x minus image of u. And this is a closed so this precisely is a closed subset because u is open in the y. So pre-image is open in x. And this means that it is closed in x. And so you can also do the induction. Yes, so just proceed by induction. So you reduced it to the following case. So you are searching now. So xn now sits in some z, which is x without f inverse of u, and it maps to y without u to some w, and z is closed. So this is closed. So that means that if we by induction on dimension of x plus dimension of y, so xn is closed in z. So this means that just xn is closed in x. Yeah, because it is closed in the closed subset.
Because dimension of z is
Yeah, because so it is because x is reducible. I take so just from the beginning I take x to be reducible because it is sufficient to check it for component wise, and then I just take dimension of z is since x is irreducible. So since x is irreducible. So z cannot be one of the components, so it has smaller dimension. So then dimension of x is smaller than dimension.
I didn't understand earlier that if it can be one component, so as well.
I mean, yeah. So just so dimension of just to erase something. Let me. Yeah, so this is really just depends on this chain. So you have if you have the variety that you can put inside Z, and it is irreducible. And and the X is irreducible. Then you see that if you have chain, so some chain of the varieties then ends in Z, so this gives a chain for X.
How do you obtain that Z is irreducible?
I mean, just take any reducible component. So here you can take any reducible.
So you will
So
get fine
it is,
so you will get fine tuning of course.
Yeah, so Z is just actually, so Z is the union of Zi irreducible components, and so dimension of each Zi is less than dimension of X. So if you put this Z here, which is irreducible, this means that you have a chain here that is also the chain for X. So this means that dimension of Z among all chains that are contained in X, so you can always extend it to chain for X. So it's less starting at a given point. So you fix this point, so it is less than dimension of X. And of course it can happen that why I'm just specifying that X is irreducible, it can happen that if you are thinking about X, so that which has two irreducible components, you can separately look at chains at each irreducible components, and this would pose a problem.
Why extends close to Z? Why extends close to Z?
Why what?
Why exam is closed in Z?
In Z by induction. I mean dimension, by induction and dimension of Z is less than dimension of X. You apply the induction statement for Z and W, and Xn is a subset in Z, so it is closed in Z, and Z was closed subset.
So in some point we find Z such that Z is equal to Xn. No.
So we reduce and reduce Z on each step. It is a sequence of closed subsets. And so actually what we are doing is the following. So you are just so you if you have Xn here, if it is it doesn't, if the fibers doesn't have expected dimension, then you can throw away an open subset here U and the preimage of this open subset. Then you pull this Z and again apply the procedure. You look at Xn, either it has expected dimension and it is everything, or it is everything because you have this kind of inequality. Yeah, so if it is not everything, again you take open subset here and you throw it away and you look at the smaller closed subsets. And in the end of the day, you have a sequence of closed subsets where you have Xn, and this terminates when this closed subset is just equal to Xn. So this is precisely the case when the termination of occurs. So this can be stated as just as a construction. So how we are searching?
Does Z becomes a new X and F and Z becomes a new Y?
Yes, Z becomes new X, and so the W becomes new Y, the complement. So just apply, so by induction on dimension of X, apply it to Z, so applied to the map from restriction of the map from Z into W, we get extent that sits already in Z is close to that.
And Z is irreducible, right?
I mean, you can pass to a reducible. I mean, here Z is not. It can be not irreducible, but you can pass to reducible components in order to compare dimension.
Okay.
So, at any case, its dimension of any its reducible components will be smaller than dimension of X, because X was taken to be irreducible. But this means that when you proceed by induction, you should be able to decompose again the Z as just it is the union of some reducible components. You apply the theorem to each reducible component separately. I mean, as another. So, and why we actually needed the Chevalier theorem? We needed to prove the following statement. This is constructibility of the image. So, theorem constructibility. And it is why we really bother about constructible set. Of image. So if F is a morphism of varieties, so it's a morphism of algebraic varieties. Then image is constructible. So then f of x is constructible. So this is why I actually bothered in the theorem that I have stated. I really bothered to take the closure of f of x. And the proof is very easy here. So you have, I mean, for constructible set, you have to just to decompose, to be able to decompose your set to the union of locally closed subsets. So if you throw away an open subset, so this so you can do the following procedures. Yeah, so you consider the morphism. You take so here you have take subset where you have expected dimension. So take U for which you have expected dimension, open in Y, of such that the fiber the dimension of the fiber has expected dimension. Then you do the following. You take this U. Yeah? So you see that U is precisely in the image. Yeah? So what we needed to know that U is in the image. And then you know that the complement, so you can pass to the complement. Yeah? So you can pass from X to through image of U, and you put it Z, and you can pass it to Y without U. So it is again W. So you have the map between algebra. So this allows you to say that the complement is also closed subset. So it is an algebraic variety. So this is algebraic variety. And notice that since it is so you can pass to irreducible components from the beginning, so pass to irreducible components. So then, of course, you can take the union of the subsets obtained. Yes, so you're proving that for each irreducible component, this is constructible, and then you are taking. So so if x is obtained as the union of irreducible components, then of course it is clear that just the image is the image of the irreducible component. So we prove that this is, we have to establish that this is constructible.
That local closed sets appear.
Just a second, to take the union. I mean, so now I have to, now I know that f of z is just, so now I know that f of z is constructible in W by induction. So just is constructible. In the W. So the claim is that just you are doing the following.
I don't understand how did we take such U.
I mean, by Shirella continuity.
In our theorem, the morphism was dominant.
I mean, pass to just in order to say that, yeah, so, yeah, again, if you have x and y, what you can do? So you can, if they are irreducible, then you decompose it into irreducible components, then you strip your morphism to each irreducible component, and then pass to the closure. Yeah? So you can pass to xi, and here you pass to the closure of the image.
So now it's dominant.
And now it's dominant, and this is well-defined this is well-defined algebraic
And
variety.
if we prove that image is constructible in closure of image, then it will be constructible in Y.
Yes, so this is what I wanted to say. Yeah, so if you have f of z, it is constructible in W, yeah? So, and W is closed in Y. So closed in Y. So this means that so you have the following. So you have f of z. So here it is constructible, and here you have y is closed. So f of z is constructible in y. It's constructible in y. And here you do just a very stupid thing now in order to prove f of x is just the union of u and f of z, which is also constructible. So if you, I wanted also to say here that the dimension of z is strictly less than, since x is irreducible, was taken to be reducible, then dimension of z is less than dimension, strictly less than dimension of x. So since x is irreducible, so you apply induction. So by induction, applied to z. So just applied to z and w, you see that f of z is irreducible.
So, did we prove that image is just open subset and some points? Or
No, I mean that, so the problem is, yeah, so the problem is that what you do, yes, so you have taken open subset, yes, so then you pass to the complement, then of course here you have closed subset, then again you take open subset here,
Open.
Yeah, so just you cannot guarantee, so that,
It's not open in.
yes, you cannot guarantee that the union of this open subset and this open subset is open inside the whole thing. Yeah? But the trick is that you just you do not. I mean, because for this the example that we have really shows what can happen, what the things can happen here, and yeah, I mean, if you know that on each step you have open subset, yeah, so then you know that in the end of the day you will have the images open, which is not that we expect. Yeah? So if at each step applying our procedure, I would be taking the open subset. But notice that there was a question about so how we reduce to our theorem. So it can happen that so when you pass, in order to reduce to Chevalier theorem, you have to take the union of xi and take then take each xi and take the closure of the image. So notice that when you are so what happens for a fine line and a fine line here? Yeah? So what happens with this thing? Yeah. So when you pass to the open subset here, U. Yeah, so of course you throw it away, and you get what? You get this line where this line is met. And here notice the condition of the Chevalier theorem, that as we stated, that it failed. Yeah? Because so this line maps precisely in the point, not dominantly. So in order to apply Chevalier theorem, we have to reduce, so we have to take the closure of the image, which is precisely this point. Yeah? So that means that if on each step the map was always dominant, yeah, then just we would have proved that our subset is open, because at each step we are taking the open subset in the closed. So we are taking the complement and the opens. So we are taking the complement, we get closed subset. We are again throwing away an open subset. So the complement is closed. So at each step the remaining, if you know that the map was dominant, so you have this open subset, you can take the open subset at each step. Then you just have, in the end of the day, you have the remaining part where you do not have a map, it is just a closed subset. But here you have an operation that you have to take the closure of the image. So this means that on some steps you are passing to the closed subset. Here it can happen that you are passing to the closed subset of the closed subset, and here you are taking the open subsets. So so at each step you are passing to the complement of the open subset, a closed subset, and the complement of the open subset. Then again you take an open subset and just the complement, which is closed, the closed subset, and the complement, etc. Ну, то есть как бы на каждом шаге, то есть у нас процедура не переход каждый раз к открытому множеству, а переход к открытому множеству, и иногда нам приходится брать замыкание нашего образа. Да? Из-за этого мы переходим к открытому множеству, дополнение к открытому множеству замкнутое, в нем надо перейти еще раз к замкнутому подмножеству и так далее. Из-за этого возникает именно конструктивное подмножество. Понятно? И вот на этом примере это прям видно. Да? Хорошо? Okay. So while we needed this, so yeah, so what we know about So properties of constructible set. Constructible sets. So we shall need the following property that just if X is constructible, then there is an open subset in X such that so which is open. Yeah. So just let me do it like this. So suppose you have X as variety, algebraic variety. So you are taking the subset X, which is constructible. Then there exists an open subset. There exists locally closed subsets, locally closed subset. So, which is just the intersection of Z and some open subset. So, just such that just the closure of U is equal to the closure of Z. So Z can be not closed, so we can take a closure, and I claim that there is so locally closed subset, so constructible subset is the union, finite union of locally closed subsets. But there is one closed subset, so the one locally closed subset which is dense in Z. I mean, just I mean, if you are taking, so example, let me. So this is will be exercise. So this is not complicated, but you can have the example. So the example is that again our beloved example. So here you have this point. So this is constructible set itself, but there is an open subset which is so which is just this set without a line, and this subset has the same closure. Yeah, so this is X equal to, so this is Z, and the X is just a finite space. So you see that the closure of Z is equal to the closure of U, and which is just a finite space. So why do we need this theorem? This is in order to see what happens with orbits. So proposition. Just orbit is Gx. Yeah, so like we have an action, so G acts, so algebraic group that acts on X, algebraic variety. Then I claim that orbit Gx is open in its closure, is a locally closed subset.
What about Gx is open?
Huh?
You said Gx?
Open, I shall say it's a locally closed subset. Gx is open in the closure of Gx and X.
What about обмотка то?
Ну а какая это алгебраическая группа? Это группа Ни. Ну, в смысле, даже не группа, не подгруппа Ни. Вот.
Нет, ну в смысле.
Ну, в смысле,
это действует на
обмотка Тора это даже не подгруппа Ни. Ну, в смысле, что...
Есть действие окружности.
Но оно не алгебраическое.
Ну да.
Ну да, даже, чтобы говорить об окружности, еще должно что-то. Вот. Ну, в контексте группы. Вот. Вот. So, so this is quite important thing because yeah, and this is and your example. So your just objections shows that that this fact is not trivial. So that we're going to prove. So notice that Gx is an image of G and to X, so that G maps to Gx. It is an image of the orbit morphism. So you know, so this subset is constructed. Subset in Gx in X is constructed. Then, since it is constructible, there will be just open subset U that sits in Gx, which is open, so U open in the closure of Gx, and so they have the so this are both just they both has the same closure. But notice that to this open subset we can apply G. So then G, if your element G, action of the element G of Gx fixes Gx. Notice that it fixes also the closure of the orbit. Yeah, so also G fixes the Zx, the closure of this orbit, and the reason is purely topological. I mean, it comes from just definition of the closure. So let us recall that the closure is just the intersection of the closed subsets, so V that contains Gx. And if you have the element, so V is closed. Yeah? It is the definition of closure. Yeah, more generally, if you take Y, so on it is a G invariant subset. So I shall need this observation explicitly. So this is just intersection of, again, of the closed subset. It's containing Y. So this is closed. So you notice that if you have an element of G, then Gy tilde Gy overline sits in Y overline. This is just because if you have a V that contains Y, then if you apply G, so Gv, contains gy and gy is equal to y. So this means that gy is containing y, so this intersection is the same. Yeah? So this means that if you apply gy tilde, it is just intersection of gv, and it is the same subset. Right? So you just take the intersection over different indexes. Yeah?
This position, I mean, I understand somewhere somewhere.
Вот это, да?
Нет, даже GX, GX.
Ну, если, ну давайте заметим, что ну, как бы образ G X, ну, от орбитный маркизм, он конструктивный, да? Значит, найдется такое, ну, такое подмножество, которое открыто внутри замыкания, что, ну, оно, во-первых, открыто, а во-вторых, их замыкание U и GX совпадает.
А орбита неподвижна.
Да, но орбита, ну вот как бы теперь я хочу заметить, что замыкание, ну вот сама орбита, она неподвижна относительно действия G. Поэтому я хочу заметить, что замыкание неподвижно.
Ну это очевидно.
Ну это очевидно, ну вот как бы, ну потому что, ну надо вот это определение.
Потому что коммутивы взять из замыкания и непрерывная функция на самом деле.
Ну а при чем тут непрерывная функция? Мы должны,
действовать непрерывной функцией.
ну как бы мы же должны это алгебраически переформулировать, ну топологически. Ну а топологически у нас никаких непрерывных функций нету. Ну, у нас есть отображение. Ну, как бы, ну, потому что y это пересечение замкнутых содержащих y. Ну, замыкание y это, ну, понимаю, как бы вот так, да. Ну, это очевидно, но это нужно написать вот так, да. Вот, so this means that since g fixes gx and preserves the property of being open, then this means that gu is open in gx overlap. Yeah? And this means that you can take the union of this open subset. So the union of all elements of the group is open in Gx, but of course if you take all the union, it of course contains, it is equal to the order.
Do you mean that U doesn't necessarily preserve
The U is not, could be not, a priori it could be not preserved. So the idea is that the following, so you have a Gx, you have to take its closure, then you have to add something here. But so there is an open subset here, U that is open inside its closure. Yeah? So you can move it, it could be not invariant, so you can move it by G. And when you take all the union of over GU, it will be still open, the union of open subsets in open, but it will cover all GX because it is just an orbit of one point. Yeah, so it is just all the translations are covering. I mean, the translation of one point are covering the orbit.
So this is the union so this closure is the union of open sets.
This closure, the orbit is the union of open sets and the closures.
And what is it about
This?
section? Yeah.
Yeah, this is just a definition of what is closure. And so the closure of a subset, it is intersection of closed subset. The closure of any subset, by definition, it is intersection of closed subset containing this subset.
Okay.
So if this subset, if Y is invariant, then I claim that the closure is G invariant. This is because if you apply it to G, so this is applying G in the argument, so you just permute the set of closed subsets containing your Y. Ну, то есть, как бы, это наоборот. Вот тут мы разносили открытое подмножество, а тут у нас есть Y, и вы его представляете как пересечение, ну, вот таких ЖВ. И если вы, как бы, берете, ну, вот, вы взяли множество, которое содержало Y замкнутое, но если вы Y сохранялось G, то вы G примените, это тоже одно из этих множеств. И все объединение этих множеств, оно сохранится, потому что вы можете как G применить, так G минус 1.
Пересечение.
Да, пересечение множества. Ну вот вообще вот эти, я имею в виду все множество подмножеств V таких, что ну, они содержат Y, оно инвариантно относительно G, потому что как G можно применить, так и G минус 1. Yeah, so now we have to just discuss the properties of subgroups. So,
Was the property about was it all the proof that the orbit is constructible?
the orbit is constructible with this theorem on the constructibility, because it is image. So you just take the following set, the following variety, and look at the image under action. So any orbit is the image of this variety under the action.
What was the last property about? Exactly.
Давайте по-русски уже.
Вот G.
Потому что я потерялся, что...
Вот последнее
Да.
свойство, потому что Gx, образ G, Vx, следовательно, множество сконструируем, это мы уже доказали, но эти
Ну, у вас исходно уже... Нет, мы вот здесь предложение мы доказываем не конструктивность орбит, а то, что она открыта в своем замыкании. Вот.
То есть она и открыта в замыкании, и конструктивна.
Но она не только конструктивна, она на самом деле локально замкнута. То есть это пересечение открытого и замкнутого.
То есть мы доказали, что она конструктивна от того, как раз потому...
Нет, мы считали, мы приняли нашу теорему, ну как бы с теоремой Шевале мы вывели, что образ любого морфизма конструктивен. Но теперь орбитное отображение, это образ многообразия G(x) при морфизме действия. Поэтому мы воспользовались предыдущей теоремой, чтобы понять, что оно конструктивно.
Ну потом типа конструктивно бывают какие-то разные точки, будут на них G все равно действует. Смотрим, ну это типа все одинаково.
Да, ну как бы вот, ну вы правильно идея. Что как бы, ну в чем проблема, что конструктивное множество получается именно объединением каких-то своих кусков. Ну вот как бы вот за счет действия группы эти куски как бы перемешиваются. То есть вот бывает, ну вот что у вас не происходит именно вот эта ситуация, когда множество конструктивно, но не локально замкнуто, что у нас нету кусков разной природы за счет действия группы. So,
Ну что группа действует примерно.
да. So I want to prove the following. So just take so claim. If so, how to generate the group? Yeah? So claim that suppose G is algebraic. Well, let it be irreducible now. Algebraic group. And you have two open subsets. that G is generated, so you can take pairwise products. So I claim that G is generated by this pairwise product. So U times V, where U is V. So here, of course, you can take even larger subsets. I mean, some constructible some dense subsets, constructible dense subsets. So this can be taken to be constructible subsets such that closure of U is equal to closure of U. I mean this, notice that this doesn't, so the constructibility here is quite important because you can just, you cannot just take two dense, even the risky dense subsets such that they generate the value products. So who can give me an example actually? So count example. So to the statement then, you cannot say that it's not so easy actually.
And can you
Yeah,
give
so-
an answer, for example, when it's not enough to take one subset open, not product of two open
Ну так
subsets?
это тогда У и У. Нет, ну
Not when
нет, в смысле, можно просто подмножить. Это же попарное произведение. Любая группа порождает. Нет,
Сейчас,
то, что вы говорите, это взять У и У. Ну, такие произведения.
Сейчас, она равна как множество,
Не, ну у вас может быть просто открытое одно что-то в группе. Ну, в кассе с дырочкой вы кинете какой-то набор. Порождает. А я говорю, что G равна просто попарным произведениям.
То есть, когда это произведение, это как
Ну
множество.
а то, что вы говорите, это тогда U равно V, ну я допускаю. Да? То есть вот G порождается попарными произведениями.
Нет, вот G равно множеству.
G равно
Вы
множеству.
сами говорите, порождается, я думаю, порождается как
Ну да, ну в смысле G равно множеству их попарных произведений с двух элементов. So, let us...
For example, is maybe rational algorithm.
Нет, ну как бы там оно не конструктивно. В смысле, yes, so count example. Да, давайте, скажите. Только C надо, да? Ну, в качестве группы C.
Это звездочка.
Ну да, ну хотите C созвучить.
Еще раз, к чему контрабизант?
Ну что обязательно У и В должны быть хотя бы
Хотя бы
конструктивны.
конструктивно, то есть это вообще хотя бы что-то.
Но они просто дело в том, что если у вас
А.
что не алгебраическое, можно взять его замыкание позариста.
Я просто...
Yeah, so the claim is that if you just consider two subsets without any structure, you can take the risky closure.
So maybe it's
So
something...
the risky closure is defined this way. I mean, Y shouldn't be have any structure, so it is just a subset.
So the risk closure of set of all rational complex numbers is, of course, all complex numbers, because if polynomial takes zero values.
Yes.
all these complex
Yeah, so you just take the lattice, yes, so Q plus
IQ.
IQ, and you can take this, so this is the risky dense. I mean, so let us put additive proof.
No problem.
Yeah, so, and just for convenience of writing it. And then this will be just, this will be dense, the risky dense, because this are infinite points.
But they are not open.
Yeah?
Are they open?
We give counterexample.
Yeah, we're giving
Constructible
So, and notice that if you take the product, so the sums of this subset, it is still the sum, it is still the same subset. So it cannot generate, you cannot write down the element as the product of
So every open is dense, so constructible dense is weaker than open.
Constructible dense is could be weaker than open, but via the exercise, since G is irreducible, it is reduced.
We have open
Yeah,
inside
yeah,
too,
yeah.
so no.
So it is just a statement. I mean, this is just variant of the statement. More or less editor. Yeah? So. А когда мы заканчиваем? Я просто...
6-20.
А, 10?
13 ночи.
Точно, да? Целую. Ну, хорошо. Не, просто тогда надо заканчивать. Yeah, so if you have, so let us, we want to write down G as the product, so the element of G as the product of two elements, yeah? So let us apply G inverse U, yeah? So to U, I mean the inverse as an element. And let us try to intersect is with V, yeah? So notice that these are two open subsets, and they are both dense in G, so they intersect, so since G is irreducible, so that this intersection is not empty. Then there is H, yeah? So there is H in this intersection, so this means that we have written H an element of V, we have written it in the form G minus 1 times U. So this means that G is written in the form UH inverse. So it is actually trivial state. I mean, at least one statement should be almost edited. But notice that it is quite important to understand that set theoretically there could be some complicated.
Again, when you are intersecting these two sets, why the intersection is empty?
Not empty.
Not empty.
Because they are complements, so this means that G is a union, so if
so G contains disjoint union of open sets.
you know, if U1 and U2 open and have empty intersection, then G is a union of two closed subsets. Well, X is a union of two closed subsets, so they're both closed. And X is was assumed to be reducible.
But here, I mean, H inverse is not in V, so probably you should
Yeah.
G inverse here with V inverse, because V inverse.
Yeah, V inverse is also open. Yeah, sure. Yes. Yeah. So yeah, thank you very much. So this belongs in V inverse. So the V inverse is also open because of the continuity of taking the open in G. So yeah, so then I wanted to speak about just how we can generate the subgroup. So suppose you have H inside G, so G is algebraic group. And H is arbitrary subgroup. So it is not closed variety. So it is just, for example, we can take this C and Q plus Q that we have raised. Then I claim that H is H the closure, the risky closure, is a subgroup, is algebraic subgroup, and the second, it is almost so this is constructibility statement that just if H is constructible, if you know for some reason that H is constructible, then H is equal to, H is already closed.
So there are no subgroups.
Which are not algebraic, yes, so, and are not closed. I mean, constructibility is too strong a statement. It implies automatically that it is closed. So, position, yes, proof. Yeah, so notice that what we know, yeah, so we already noticed that if H times H sits in H, yeah, so for any element of H. So you know that H also preserves the closure. But also, so this means that H, so in particular, you can take all elements of H, and this implies that H times H tilde overline sits in the closure. And this implies the following, that now you can take H tilde from the closure. And this statement can be rewritten as H times H tilde sits inside H tilde. But now we can take the closure with respect to H. So this means, so we're using the following property, that if Y sits in some doubly closed subset, then H times, so then Y closure, so this is already a closed subset, so this means that you can take, this is H invariant closed subset. So that and closed. So I can take a closure of Y, and it will be still sits in W. So if you have this subset and the closed subset, and this closed subset is already invariant, then the closure of Y also sits. So this is evident actually.
I don't understand
Yeah, so
this claim.
the claim is evident. So I wanted to say that if this happens, this is closed already. So this means that H overline times H tilde sits in H. If you take, if you take H and you just applied one H tilde. If you take the closure of H, because H is homomorphism, you can just you will have this. You can take the closure of H.
If by claim.
Yeah, I mean that if now Y, H sits inside H tilde, then I claim that, and the H tilde is fixed by, is preserved by H. And so I can write down like better like this. So H sits in H tilde inverse H tilde, and then this implies this is closed, and this implies that H tilde sits in H inverse H, and this means this implies again this kind of this. And this happens for any H tilde inside H tilde, so this proves that H times H is equal to H.
Why is it so that if Y lies in H invariant subgroup, then the closure of Y will lie?
Yeah, because Y sits in H tilde inverse H,
Yeah.
and this is closed subset.
Okay.
This is closed. H is continuous, so
So we don't even need that it's invariant.
Why
Just
will
that it's
Y
closed.
yes, yes.
it just knows that the group is inside the closed subset. Why will it be closed? So closed. Why the closure will be closed? Ah, I see.
No
Just
problem.
because if I take the closure,
You can take one of these subsets and move the closed.
okay, I see. It's like if an open subset lies in a closed one, then the closure of an open subset will lie in the closed one. That's the growth.
Ну там это еще проще. Там просто там не в открытом вы лежите, просто если вы уже лежите в замкнутом, то замыкание важно множество держит. Yeah, and the second part, so proof of the second part. Yeah, so notice that so you have taken H, so you have taken its closure. Notice that this is constructible. Then there exists, again we shall use that property that there exists U an open subset in H, such that, so it's open in the closure, such that U and H are equal. And now you recall that H, this group is generated by two open subsets. So now recall that this is algebraic group.
So it's just generated by open
Yeah,
subset.
so it is just generated by this open subset, by the previous thing.
Excuse me, but it's not, it can be not reducible.
Yeah,
We
but
don't reducible about this open subset and all, because it's not formally reducible.
Yeah, but so for this open subsets, you should take dense open subsets.
Dense
Dense.
subsets and unshift dense
Yes.
There is open set and dense open set inside it, and this will generate in not reducible case.
Okay. Yeah, so yeah, I think we'll have to stop here. And next time I shall give you criterion of saying that the group will be generated by some constructible sets, and this will, the claim will be that the group that you obtain is algebraic. So this is some kind of criterion that you start taking your group, just you can generate it by a collection of subsets, and still what you get is still algebraic group. So this will be important criterion for us, because for the following, so we intend to speak about solvable groups, and for solvable groups you probably know that, yeah, so that the problem is in Lie group theory that congruent is not a group in general. So it's a group, but it's not a Lie group in general. And this suggests to pass to some special things like modes of closure if you want to speak about Lie groups, but if you want to speak about algebraic groups, luckily this is algebraic something, so we shall spend some time improving this. Okay. So thank you very much.
Там получается студенты знаете, замечательный вас создать чат вопроса.
Ну, как обычно,
Создаете чат. Вы знаете, как студенты, что есть.
ну я